Today we're going to be talking about ordering sequences and their limits. Okay, we've talked about how to do arithmetic with limits, right? Sort of doing some algebra, combining sequences in certain ways, and what that tells us about how we can then combine their limits to find limits of these new sequences. And now we're going to deal with ordering, which is really related to inequalities. So here's an example of the kind of thing we're talking about. Let's say that a sub n is the sequence n over n plus 1, and b sub n is the sequence n over n squared plus 1. And so we can say the following. A sub n is less than or equal to b sub n for all n greater than or equal to 1. Right, so b sub n generally has the denominator is greater than or equal to the denominator in a sub n, and so this goes the other way. Sorry, so actually, right, my inequality is doing this. Right, a sub n is greater than or equal to b sub n for all n greater than or equal to 1, because b sub n has the denominator that's greater than or equal to the denominator for a sub n. And so these both converge. So both converge is the limit as n goes to infinity of a sub n greater than or equal to the limit as n goes to infinity of b sub n. Right, so if we had this ordering on the terms, then do the limits have the same ordering? Do they compare in the same way? All right, so here's a theorem to discuss some of these ideas. So this is the order theorem for sequences. So suppose a sub n and b sub n are sequences that converge to L sub a and L sub b, respectively. Okay, then here are some statements. So one is if a sub n is greater than or equal to 0 for all n greater than or equal to 1, then its limit has to be greater than or equal to 0. The second statement is along the lines of our example. So if a sub n is less than or equal to b sub n, okay, for all n greater than or equal to 1, then the limit of a sub n should be less than or equal to the limit of b sub n. 3 and 4 are essentially the same result. We're just switching around the direction of the inequality. So 3 is if c is some real number and a sub n is less than or equal to c for all n greater than or equal to 1, then the limit of a is less than or equal to c. And then 4 is the same, the exact same result as 3, but we're just, like I said, switching the direction of the inequality. So everything else is the same. We're just changing these to greater than or equal to signs. Okay, so if c is a constant and an is greater than or equal to c for all n greater than or equal to 1, then the limit of a is going to be greater than or equal to c. All right, so let's talk about how we might prove something along these lines. I'm going to prove one, and then I'll leave the remainder to you. So the first statement, let's just write it down again. So 1, an converges to L sub a if an is non-negative, then the limit is also non-negative. All right, so let's do a little bit of scratch here, specifically for this part of the theorem. So I'm going to aim for a contradiction here. Right? I want to show that the limit has to be non-negative. What happens if it's what happens if it is negative? So contradiction. Suppose L sub A is not greater than or equal to 0. So that makes L sub A less than 0. Negative. Okay, so then what are we saying? Here's a number line, right? Here's where 0 is. L sub A is less than 0. All the A sub n's are over here, right? So all A sub n are here. Okay, but we're supposed to be able to get within epsilon, right? Within any positive epsilon of the limit, right? So convergence in particular tells us we should be able to get in here. Be able to get in here. I.e., within, so how close are we going to be to L sub A if we're in that region I'm pointing to? Well, it's going to be absolute value of L sub A, right? That's that distance here between L sub A and 0. Right, so this is distance from L sub A to 0. Right. Okay, and then because we're supposed to be able to do that, and we know none of the A sub n's are in there, right? That should produce a contradiction of sorts to us. So let's try to put this down in a proof. All right. So suppose that L sub A is negative. Since A sub n converges, for epsilon equal to absolute value L sub A, which is greater than 0, there exists capital N such that little n greater than capital N implies A sub n minus the limit is less than the absolute value of L sub A. Okay, but here's something that we can say. All right, we know that we know the absolute value of A sub n minus L sub A is actually equal to A sub n. Absolute value of A sub n plus the absolute value of L sub A. How do we know that? Okay, so we know A sub n is non-negative, and we know that L sub A is negative, so negative L sub A is positive. Thus, when I take absolute value of A sub n minus L sub A, its absolute value, I can think of it as the absolute value of the sum of two non-negative numbers. And that means it should be equal to absolute value of A sub n plus absolute value of L sub A. A sub n is greater than or equal to 0, so this is greater than or equal to 0 plus absolute value of L sub A. And there we have our contradiction. A sub n minus L sub A in absolute value has to be less than absolute value L sub A, but then it also has to be greater than or equal to L sub A, which is a contradiction. Okay, so therefore it has to be that the limit of the sequence A sub n is non-negative. All right. Okay, so if everything's non-negative in the sequence, you cannot have a negative limit, because since you can get as close as you want to the limit, we'd have to end up eventually, essentially with negative terms, right? The only way to be within absolute value L sub A of L sub A in our contradiction argument is to have a negative term. Okay, so that there's sort of slightly different ways you could argue this, right? So you could show that A sub n would have to be negative as well, and that would also result in a contradiction here. Okay, so slightly different ways to find our way around this contradiction, but any way you choose to do it, it shows that non-negative terms in the sequence will lead to a non-negative limit. All right, so I would like you to think about proving the rest of this theorem we stated as an exercise. So exercise 1, prove part 2. And consider how you could use part 1 potentially. Consider what we know about how we could combine sequences, right? And say something about the limits that you get from these new sequences you build by combining existing sequences. Excuse me. Exercise 2 is to prove parts 3 and 4. Right. Once you get one, it's really very much like the other. You sort of just switch around the inequality, but prove parts 3 and 4. And again, you don't necessarily have to reinvent the wheel here. You can try to consider how you might use things we already know, results already proven, to get these results here. Okay, and then one final exercise I want you to think about. You may be familiar with something from calculus known as the squeeze theorem. So I want to state that here, and then I want us to prove it. So consider the squeeze theorem. And it's all about a sequence getting squeezed between two other ones. So if A sub n, B sub n, and C sub n are sequences with A sub n less than or equal to B sub n, less than or equal to C sub n for all n at least 1, and AN and CN both converge to L. Then Bn gets squeezed between the two, right? That's why it's called the squeeze theorem. Then B sub n also converges to L. So there are a lot of conditions, right? Most of this statement is just a lot of conditions, saying something about the sequences, saying something about convergence for A sub n and C sub n, and then the conclusion is that B sub n has the same limit. So there's two parts to this exercise. So one is the following. So A is we can't just use part 2 of the theorem we just stated to prove this. So why? Right? It sort of seems like take part 2, just apply it to AN and BN, and then apply it to BN and CN, and then we're all set. Right? You have that BN would have to be greater than or equal to L and less than or equal to L, but we can't actually apply part 2 from this theorem we stated at the beginning of the video, and I want to know why not. And then I want you to go ahead and prove it. So consider going back to the definition of convergence to do this. So prove the squeeze theorem. Okay, use what we know about A sub n and Cn, and that should be enough to figure out something related to Bn.